Hi, everyone. Thanks for joining this session. During this session, we're going to talk about unleashing generative AI in real time with Apache Pulsar. Before we started, let me make a quick self-introduction. My name is Nenlu. I'm currently a senior tech lead at Native, and I'm the founding member of Native, joining in 2020, and I'm a committer of the Apache Pulsar project. I currently lead the platform team, which focuses on the development of Apache Pulsar project and the integration between Pulsar and the whole big data ecosystems. So before I joined Native, I was a senior software engineer at Twitter, mainly focused on the real development of real-time processing frameworks. So this is my brief background, and yeah, let's get started. So for today's talk, the agenda would be roughly like divided into three big sections. The first section would be a general introduction and the investigation of the GenAI and some of the problems or issues we identified. And the second section would be like a introduction about the Apache Pulsar project and some of the key features we think it was useful for the GenAI use cases. And thirdly, we will briefly looking into some of the examples for how we can utilize Apache Pulsar to power the GenAI use cases. So this will be the agenda, and let's get started. So first of all, GenAI. What is GenAI? I think based on the definition on Wikipedia, GenAI is like generative artificial intelligence, and it's artificial intelligence that capable of generating text, images, videos, or other data using generative models, often in response to prompts. And the GenAI models like learn the patterns and the structure of their input training data, and then generate new data that has similar characteristics. There was a very interesting view on top of the GenAI, that is, we can consider that as a compression of the real world. So people are feeding like petabytes of data into the model and then generate hundreds gigabytes size of the model with like 500 million or 7 billion like parameters for the model. And once we have this model, we can consider it as a compression of the actual data. And once people or users feed in some kind of prompts, the compressed model would be generating the results. That is a very interesting kind of point of view. And as we mentioned that the GenAI can generate not only text, but also images, videos, and even some complicated models, they can also support all these like different types of files at the same time. So here are these typical use cases for different types of the output. Like for text, we have GPT-4 developed by OpenAI, or Llama open sourced by Meta, and also DVRX from Databricks. For image models, we have the DALL-E or Midjourney or Stable Fusions. And for the video, we have Sora, which is quite impressive if you watch some of the demos recently, Runaway, Pika Labs. And there are some pioneering work on the multimodal area. So I think currently, like the most useful case will still be like text, but people are exploring the image and the video GenAI area. Although there are some kind of problems, let's say for videos, there are the consistency issue and the limit of the video length. So either way, these are the typical use cases, but not limited to only these ones. If you are interested, you can search online more and find out more like companies doing all these GenAI works. So since we are an infrastructure company and we are all like infrastructure engineers, we are more interested in the underlying pipelines. How does it work, and what are the problems may exist? So based on all our initial investigations, we found that for GenAI pipelines, it typically like consists of the following stages, including the data foundation, which mainly focusing on collecting all the data and preparing all the data, make them ready for the model training. And second phase will be like training the actual model, which may require a lot of like GPU resources invested. And after the model is trained, there probably will be some kind of evaluation to identify or measure the performance of the model. And if everything works fine and it's okay, then it will be passed on to the orchestration phase that will actually train this newly trained model together with all the other services to providing an actual service for users like ChatGPT, for example. So the reason why we highlighted the data foundation and the orchestration phase here is because we think that Pulsar can bring extra ability to the pipelines in these two phases. We will go into details further in the later of this talk, but let's move on for now. So for the data foundation, so as I mentioned, that it can be further divided into three sub operations. First of all, it's a collection, and in terms of the collection, some of the behaviors we observed would be user will manually upload some of the files into a given Google Drive or into some given locations. And also there will be a web crawler which will scraping the web content available publicly. And also there will be some kind of pipelines continuously collecting the data from different sources for later stage processing. And for the preparation, it's more about how to improve the quality of the data we just collected in the previous phase. Normally it will be including cleaning the data, remove all the anomaly data, and the chunking, which basically divides all the data into different small chunks, and then maybe converting them, calling some kind of embedding services or utilizing some of the embedding models to convert all these text or image data into certain type of embeddings, vectorized representation. And lastly, we will after all these preparation, we would be store them in some vector database or lakehouse systems for so to make sure that they're ready for the next stage for training the model actually. For a typical data pipeline, it will be the abstraction will be look like this. From heterogeneous data sources like text, PDF files and web pages, and there will be some kind of extract and load phase, which basically gather all these files, all these content from different places and feeding into the pipeline. And once it was in the pipeline, we can do a lot of different type of transformations, just previously mentioned, chunking, embedding, and eventually after the cleaning up, we can load it into different data storage systems. So we will be looking to more concrete examples in the following, but for now, I think that should be good enough for us to understand the data foundation pipelines. So I think during our investigation, there was there are two very important principles come out, and also I want to share with you. First of all, it's garbage in, garbage out. So if you have a flawed, unbiased, or poor quality data information to train your model, and eventually you will probably get a model that produces a result or output of similar garbage quality. And secondly, it was proposed by the OpenAI researchers, that is the scaling law. So basically it says that the law scales as a power law with model size, dataset size, and the amount of compute used for training. So in one sentence summary, the more high quality data, the better model performance. And that's why we think that utilizing Apache Pulsar can help you improving both improving the data quality via ETLs and cleanings, as well as collecting more data using the real-time pipelines, so that in the future stage you can have a model with better performance. So our next stage we just mentioned is the orchestration. So this orchestration is actually the model serving phase that it's a component that's responsible for managing and coordinating the various stages and the components involved in the generative AI workflow. Here are four very common orchestration frameworks we found. One is LangChain, Llama Index, Haystack, or Hugging Face. They all have their own pros and cons and focuses on the different use cases. So if you're interested or want to try that out, I would encourage you guys to check the website for these frameworks and see how it works with your use cases. So there was another point was to mentioning is the new architecture for helping for users to improve their model result, that is called RAG, the Retrieval Augmented Generation. So we know that training an LLM model would be very time consuming and money costing. And in order to improve the quality for that and reduce the cost, people proposed some way called fine-tuning. So you can view that fine-tuning as small steps to tune the model based on the existing LLM models. But still, like fine-tuning would require additional resources and need more time, and it won't be able to take the input from the most recently generated data, but like we only have data up to the when we do the fine-tuning for this model. So that's where like IAG came from. The workflow looks like this as we show on this slide. Basically, like there will be some kind of retrieval or ingestion pipelines that continuously like scraping or getting data or documents into the embedded model, and the embedded model would convert all those inputs to document embeddings and feed them into the vector database. And in the same time, like when users submit a query or ask questions via the user applications, you also go into these embedded models, and the query and the embedded queries will be sent to the vector database. So once we have all these information, there will be an orchestration framework that providing both the prompt and also the query enhancer context into the LLM model, so that like the LLM model can generate a response by combining the user questions as well as the recently ingested documents from the ingestion pipeline. So that's how IAG works. And the beauty of the IAG is like it both, first of all, it serves like the model with, serve the customer request with the most recent data. And in the meantime, it doesn't require a lot of like fine tuning or retraining the whole model, which reduces the cost as well as the time to market value. Okay, so I think that's a very brief introduction of the GenAI, some of the pipeline stages, and some of the interesting architectures or solutions people proposed. And moving forward, I think we will like have a briefer review and introduction about Apache Pulsar, what it is, how it does, and what are some of the key features. So for Apache Pulsar, it's an open source distributed messaging and streaming platform built for the cloud. First of all, it's an open source project, which means that you can use that for free. And since it's a distributed system, so it can scale like across like hundreds of nodes, like based on your actual like traffic flow. And also like one of the very interesting part is it has providing an abstraction to unify the messaging and the streaming together, so that with this one systems, you can actually have support like both use cases supported by the RabbitMQ, as well as some kind of log ingestion services supported by Kafka. And then lastly, it was built for the cloud. That means like it has like a separation of compute and storage architecture, and it can be scaled independently from each other within the cloud environment without any downtimes. I know like one sentence may be too abstract for people. So this is the visual map, like how the Pulsar works actually. So we will have like Pulsar brokers in the middle, which is acting as the servers for receiving or sending data. And on the back end, we will be having the bookkeeper or bookie to persistently store the data received by broker. And then also, of course, there is the metadata service or the zookeeper for coordinating all these things and manage the metadata for this topic. So these are the server side components. But from user perspective, what people actually cares about is actually producer and consumers. So the producer basically is like generating data and pushing all these messages into the brokers via the abstraction topic. And the consumers, they can talk to the broker and say that I want to consume messages from this specific topic, and that's it. That's how the customers can set up the pipeline to produce and consume messages to brokers. So I think the most important like 4 pillars of the Pulsar project is actually can be abstracted here. That is, first of all, it's of course the messaging, which is supports the PubSub use case and data streaming use cases with multiple clients like Python, like C++ or Java. And also it has a persistent layer that which serves as the storage, that you can also like have the tiered storage functionality to work with the Pulsar systems to save your cost and save your data into object stores like S3. And in addition to that, Streamnative also offers a lakehouse storage abstraction, which can even better automatically integrate your data with the existing lakehouse systems. And of course, it comes with a Pulsar functions framework to do some kind of trivial computing jobs. And in the follow-up examples, we would see that how the Python Pulsar functions shines when it comes to building up the pipeline and enhancing some of the orchestration frameworks. And then lastly, also very important, I think that is the ecosystems. So it has a bunch of existing connectors to work with Pulsar, connect the top Pulsar with many of the existing data systems, as well as it also has the integration between Apache Flink and Apache Spark for do some kind of real-time streaming processing. Some of the key features here, you can also find that on the Pulsar website, but I think it worth to call out all these very useful, helpful features. Firstly, it's kind of rapidly horizontal scalability. So you can handle the increased load by scaling it horizontally. And due to the design of separation of storage and compute layer, it won't cause any service downtime during those scaling time. And also it has a low latency messaging and streaming guarantee, so that you can have as low as 10 milliseconds, under 10 milliseconds latency. And there are some of the existing frameworks or projects they don't support, but it actually comes with Pulsar out of the box is the seamless georeplication, which can help you safely store your data in different geolocations, and also the multi-tenancy support that for large organizations or for a company that's serving multiple customers, you can automatically have the isolation between different departments or different customers by using the tenants concept inside Pulsar. And also some of the things worth to call out is it has officially support multi-language support. You have clients for Java, for Golang, for Python, for C++, for Node.js, and even C#. And lastly but not leastly, we have the serverless functions and official third-party integrations with all the different systems like Elasticsearch, Cassandra, and even other more integrations between cloud vendor services and Pulsar. So with that said, based on all these great features of the open source Apache Pulsar project, with Streamnative here, we are actually providing a managed cloud service for that. So it's our offering available on Microsoft Azure, Google GCP, as well as Amazon AWS. And for private cloud deployments, you can also deploy that on Rancher or OpenShift. And these are just the infrastructure support. And on top of that, we also added a lot of enhanced features for Apache Pulsar that include the lakehouse integration, the serverless functions with different language supports like Ruslan, and also a bunch of connectors that is exclusively available on Streamnative Cloud. So this is just a quick example of how the Streamnative Sync connectors are offering. We have AWS Lambda, we have Google BigQuery, and we have Kinesis and even Snowflake. And these are some of the source connectors we have for connecting Pulsar with, let's say, Google BigQuery, with Debezium, with Kinesis or SQS. So this is the again, this is also a very high-level overview of the Pulsar project itself. What are some of the key, how it works? What are some of the key features, and what Streamnative is offering in addition to open source Pulsar? So I think now we can get into the interesting part, that is combining OpenGenAI with Apache Pulsar. So as I mentioned in the first section, that our examples will be mainly looking into the two stages of the GenAI pipeline. And first of all, that is the data preparation. We can have Pulsar applications to publishing data into Pulsar, into topics. And then we will be having Pulsar functions for chunking and doing the embeddings of these generated data. And then eventually we can also have some connectors, let's say the PyCon connector, to sync all these generated embeddings into a vector database, PyCon. And the orchestration is we are more looking into how we can converting a LangChain application into a real-time Pulsar functions pipeline. To start with, This is a more concrete example in terms of the data pipelines we just discussed in the first section. So for the data source, it actually Pulsar is quite versatile. So you can plug in like any different types of the sources like text files, PDF files, web page, pure messaging, events, apps, or even databases. And given like how you want to ingest in the data into Pulsar topics, we can utilize some of the built-in source connectors provided by the open source Pulsar project or by Native Cloud. Or you can write your own, actually you can write your own like Pulsar applications utilizing some of the client libraries to pull in these data into topics. And once the data was in topics, and we can actually launch in as many as functions we want to do different jobs, and even also like to call like different embedding services to generate different embeddings. That's very flexible. And once here, like we're only listing one functions. So once we have this function processing the data and have the embeddings do all the transformations, we can actually output it into a Pulsar topic. Again, this downstream Pulsar topic can be connected with sync connectors or can be connected with customers' Pulsar applications. And also eventually these results can be synced to external data systems. So that's kind of like how a concrete pipeline looks like. But any components here, you can actually imagine that you can spin up as many as you want, and so that to support your traffic workload and to support different business need. So moving forward, so let's look closer into the process function in our example. So basically, on the right side, it was a Python Pulsar function example. What it does is actually implementing the Pulsar function interface, and also like inside this processing method, you will like receive an input from a topic, and that input is supposed to be a URL, and then like this function would script the content based on the URL and passing it into smaller chunks. And once we have the chunks, we're actually calling the OpenAI embedding services to get the embedding using the text embedding 3 small module. And once we have the results, here we're just returning it in a string format. But imagine you can do anything you want, or even return the JSON object if you want. Also, one thing to call out is everything here is very flexible. We're just using OpenAI for demonstration purpose, but you can actually plug in any like embedding service that you want, whether that's from AWS or from other providers. So that's the function, and now let's look into how we can deploy it. Here we are going to look into the demo so that we can have a better understanding. So here I was just trying to demonstrate the structure of the Python project, and you can see that I have a depth and a src directory and a zip file. So for this submission, we will like submit it directly to some Native Cloud service Pulsar services. And in this function create command, I specify the Python zip file location and also the input and output topics for this function to process and then reproduce, and also the class name. So you may notice that there's a prep dot prefix in the class name field. It's because like we need to specify the Python file names. Okay, you can see that it was created successfully. And we can also talk to the broker service to list all the functions currently running inside the cluster. And it returns the data prep function to us. So that means like it was running. So this is actually on the backend how it looks like. We are saving all the like function information using some of the CRDs called function abstraction. And if we check the pod here, we'll see that there was a function pod being spinning up, and it will successfully like subscribe to the topics we just specified. So now what I'm going to do is actually publishing URL messages into the demo import topic, which is the Generative Artificial Intelligence wiki URL. And we can see that at the bottom, like it says that one message successfully produced. That means like this URL was produced to the import topic. And then we can actually consume from the output topic using the same Pulsar client command. And it was trying to connect to the cluster and get the result. So now it connected, and you can see that it spit out the only like single messages, which is actually embedding we received from this import topic. So now if we check into the function log, we can see that although like in production deployment, we shall not do this, but it's just for demo purpose. So I print some of the key informations here in the function part log, like including calling the OpenAI embedding service, and then like print out the embeddings we are receiving from the OpenAI. So as you can see, we have a very brief, simple pipeline spin up, which like including like producing some of the messages into the topic and having some functions waiting for processing all of those inputs, and then like and the last stage is actually and also the function will produce these results into another second topic, and the last stage would be actually connected or outputted with some vector databases. So we are like actively building out this Pulsar Python connector, which will be expected to be released very soon. So, but just as a sneak peek, we can actually spin up a Python connector using the following command on the left, or if you prefer like a more like a GUI for interaction purpose, you can also create that on Stream-native Cloud Console. So once it's created, it will like continuously like picking up all the embeddings generated by our Python function and insert it into PyCon services. But for the time purpose, I will just skip it for now. And for the orchestration, it's more about converting a line chain examples into a Python function and then deploy it into the cloud environment to let it continuously talking to different services and generating results. You can see how intuitive or straightforward it is to embed, including some of the line chain code into a Python function and then deploy it. Again, I would skip the demos for now, but let's move forward. So here are some of the references I relied on to prepare this talk. And I think this would be all for it. And if you have any questions, please feel free to ask. We are glad to talk with you and provide any support and help. Last but not least, thank you. Thank you very much for spending the time with me during this session. And thank you for listening to this investigation of the GenAI and our ideas on how we can utilize Pulsar to empower the GenAI use cases.